In the last video, I've talked about how if you have a rotating coil in a uniform magnetic field, that the flux going through the coil would have this formula with a cosine and the time in the arguments. And I've explained how by comparing this cosine graph with what we know about the displacement time graph in simple harmonic motion, we will find that the induced voltage is actually is actually related to the flux in the same way that the velocity graph is related to the displacement graph in simple harmonic motion. So that if the flux is say a cosine function, the induced voltage will be a sine function. Now in this video, I want to tie up a few loose ends that I have kind of skipped over. One of the thing is that if you look into textbooks, you will find that if you look into textbook or websites on Faraday's law, you'll find that this formula relating voltage, induced voltage, to the rate of change of the flux linkage, this equation would always have a minus sign. That there would always be a minus sign there. Now, up to now, I've simply talked about the induced voltage without paying any attention to the minus sign. I've just assumed that it's just simply the rate of change. What I like to explain now is the reason and meaning of this minus sign. Let me start again with a simple loop. So suppose that I have this loop of, say, copper wire, and I want to try to show this in 3D. So I will make this side of the loop thicker. Alright, so I'll take this side to mean to show a side of the loop that is nearer to us. Okay, so this side of the loop is nearer to us, and the other side of the loop is further away from us. So hopefully that looks 3D enough. And then we have assumed that there is a uniform magnetic field going through the coil. There's a uniform magnetic field going through it. Okay, I have mentioned a few times about a right-hand thumb rule, which we often use to determine the direction of say the magnetic field produced by currents going round a coil or a solenoid in an electromagnet. Right. Now in this case, I've not talked about any current in the coil yet, but so suppose that at first there is no current. We just have a magnetic field and a copper loop. But let's just take out our right hand anyway. Okay, take out our right hand and apply the right hand thumb rule to this picture. Now, imagine that you hold out your right hand, stretch out your right hand, and place your palm next to this coil. Okay, and stretch out your thumb and point your thumb in the direction of this magnetic field, and then wrap the four fingers around this coil. If you do that, if you do that, you will find that the thumb would be pointing along this direction. Now there is no current here yet. We're not talking about any current yet. We're just purely talking about a static case. Nothing is moving. The coil is at rest. The loop is at rest, and the field is uniform field, and it's not changing. Okay, so nothing is moving, nothing is changing. What I'm saying is that we just take out our right hand anyway and apply the right hand thumb rule to this, point my thumb in the direction of the magnetic field, wrap my fingers around the loop, and I'll find that my fingers would be pointing in that direction. Okay, so no current, just my fingers. Now, what I'm trying to say with this description is that this direction, in this direction, just my fingers, no current, this direction is by convention, by common practice, if you like, when we use equations, taken as a positive direction. Right? It is often taken as a positive direction. Now, what do we mean by positive direction? What's the meaning of this positive direction? Well, it is taken as a positive direction in the sense that if I have a voltage and a current that goes, a voltage that causes a current that goes in this direction, or just a current going in this direction, then I can give a positive sign to that current or that voltage. Okay, or meaning that if I see a value of a voltage or current with a positive sign, then the understanding is that it is going in this direction. Okay, with respect to the magnetic field. And if I see that the value of a voltage or current has a minus sign, that means we should understand that it goes in the opposite direction. Okay, so in that sense, this is if you like, a convention or a system or way of relating the direction of the magnetic field to the direction of a voltage or current in the coil. Okay, so this is considered the positive direction using the right hand thumb rule. Now let's see how we can use this to understand this now. This equation for Faraday's law, which goes something like this. Induced voltage is equal to the change in magnetic flux linking the coil divided by the time taken. Okay, and there's just one loop, so I just have to multiply by 1 and once. Now, as I said, the usual way of writing this equation that you will see in textbooks or websites, the usual way has a minus sign. Now, I want to try to understand why this minus sign comes about. So let's look at this loop now and think about the direction of the induced voltage if there is a change in the flux. Okay. Remember that arrow is not the current, it's just a positive direction. So suppose that the flux changes, right? The flux can change. When the flux changes, it can either decrease or increase. There are only two ways that it can change, or it cannot change, of course. So suppose that it increases. Suppose that the flux increases. The flux increases, then it could be because the magnetic field becomes stronger. Magnetic field becomes stronger. Then voltage will be induced, as we understand from Faraday's law. voltage will be induced. The question is, which direction will it be induced? We can answer the question using Lenz's law. If the magnetic field that we apply to this becomes bigger, maybe because I move a magnet closer to the coil, then the current must go in a direction to oppose this change, meaning the current should produce an opposing flux. Now that means that the current should produce a flux in say this direction. Okay, the current should produce a flux in this direction. So this is the magnetic field from the current. So if the current is to produce a magnetic field in this direction, in the opposite direction, to try to oppose this changing flux, what direction should the current be in? And now here's when we can use our right hand thumb rule. Take out your right hand, okay, stretch it out, put your palm next to the coil, and point your thumb in that direction. Then wrap your forefingers around this loop, and you will find that your fingers will go in this direction, opposite to that positive direction which we decided earlier on. In other words, I will get a current that goes in a negative direction. So to represent that, I should use a value that has a minus sign. Okay, so if I have a changing flux, this current induced, right? If I have a increasing flux, this current induced will go in the negative direction. Now let me write out this result. Okay. Let's say I have I make a very simple table with flux, let's see how we should do this. Okay, first we're talking about the changing magnetic field or the flux. Okay, the flux, and then we are talking about the flux itself, and maybe I'll refer to the field directly. The field, the change in flux, and the voltage. Okay, so if the field increases, I would use an arrow up to represent increase. Okay, if the field here increases, the change in flux is positive. It's a positive change because the flux increases. Now, according to this equation, then, if this will be positive, as we see here, and the minus sign means that the V should be a negative value. So V should be negative. And if the induced voltage is negative, that means that the current should go in the negative direction, which is opposite to that positive direction. And that was exactly how that was exactly what we found when we deduced this current direction from Lenz's law just now. Right? So you see that the minus sign here, therefore, gives me the correct direction of the voltage and current. So now we can begin to see why we need a minus sign here, because if I don't have a minus sign there, then my voltage value would just be a positive value that I get from this formula. But that would be wrong, because if this is positive, it suggests that the current goes in this positive direction. But we know that it goes the other way. Okay. So now let's see if this minus sign also works if I have a decreasing field and flux instead. So if the magnetic field decreases, then the flux linking the coil would decrease, so the change is negative. Okay, remember that change means that I must take the final flux minus the initial flux. So if it decreases, I must get a negative change. So if the change in flux is negative, then I have minus minus is a plus. So if I calculate the voltage using this formula, I will get a plus sign. And that should agree with Lenz's law as well. Because just now, I applied Lenz's law to the increasing field and found that the current goes in this direction. So likewise, if I apply Lenz's law to a decreasing field, now in order to oppose the decrease, the current must produce a flux in this direction instead. Okay, so if the flux to produce a field of flux in this direction, the current must go in this way. If you use the right hand thumb rule, meaning in a positive direction. Okay, and so that agrees with the positive voltage that we calculate from the formula with the minus sign. So therefore, we have, if you like, in a way, we have explored all the possible cases. There are only two possible cases, when the flux increase or when the flux decrease. And in both cases, we get the right directions for the voltage and currents if there's a minus sign there. So that explains why a minus sign is needed. And remember that it all comes down to this convention, this practice of giving a positive sign to the direction around the loop that is related to the magnetic field direction by the right hand thumb rule.